Humanity has a deadline. Whether it's climate catastrophe, asteroid impact, or the eventual death of our sun, Earth won't be habitable forever. If we want to survive, we need to leave. Not just to Mars, not just to the outer planets. We need to reach the stars. Here's the twist. We might not need 40,000 years. The race to interstellar travel is on, and it's closer than you think. And here is a question. If you could travel at 1 light year per second, where in the universe would you go first? Let us know in the comments. I'll pin the most creative answer. Now let's begin. You and I, we're living in an extraordinary moment in human history. For the first time ever, interstellar travel isn't just science fiction anymore. It's becoming a science fact. Real missions are being planned, actual prototypes are being tested, and breakthrough discoveries are happening right now that could change everything. But before we can understand how long it might take to reach the stars, we need to appreciate just how incomprehensibly vast the distances are. Because when we talk about interstellar travel, we're not talking about a road trip across continents. We're talking about crossing an ocean of emptiness so enormous that it makes every journey humanity has ever taken look like a walk to the mailbox. Let me paint this picture for you. If the sun were the size of a basketball sitting in New York City, Proxima Centauri would be another basketball roughly 6,400 kilometers away, somewhere around Hawaii. The fastest spacecraft humanity has ever built is the Parker Solar Probe. At its peak velocity, it screams through space at roughly 692,000 kilometers per hour. That's fast enough to fly from Los Angeles to Tokyo in under a minute. Sounds incredible, right? Well, even at that blistering speed, reaching Proxima Centauri would still take over 6,000 years. 6,000 years ago, humans were just inventing writing. The pyramids of Giza hadn't been built yet. Imagine launching a spacecraft today and having it arrive long after every empire you've ever heard of has risen and fallen multiple times over. This is the fundamental challenge of interstellar travel. It's not just about building faster rockets. It's about conquering distances so vast that they break our intuition about what's possible. And yet, remarkably, we're making progress. Real, tangible, measurable progress. If this kind of mind-bending exploration excites you, make sure to give this video a like. It helps more than you know, and it ensures you won't miss the next episode of our journey through the cosmos. So where do we actually stand today? What technologies are we developing that might one day carry us, or at least our robotic emissaries, to another star? Let's start with what we have right now and work our way toward the revolutionary concepts that could change everything. Chemical rockets, the workhorses of our space programs since the 1950s, are marvels of engineering. They've taken us to the moon and sent probes to every planet in our solar system. But for interstellar travel, they face an insurmountable problem called the tyranny of the rocket equation. Here's the issue. To go faster, you need more fuel. But more fuel means more weight. And more weight means you need even more fuel to accelerate that extra mass. It's a vicious cycle that quickly becomes absurd. If you wanted to reach even a small fraction of the speed of light using chemical propulsion, your spacecraft would need to be almost entirely fuel, leaving virtually no room for scientific instruments, life support, or anything else useful. The math simply doesn't work out. Chemical rockets max out at exhaust velocities around 4.5 kilometers per second. For interstellar travel, we need to be thinking in terms of thousands of kilometers per second. The gap is enormous, but don't lose hope. This is where things get exciting. Nuclear propulsion represents our next major leap. Unlike chemical rockets that rely on combustion, nuclear systems tap into the energy locked within atomic nuclei, releasing millions of times more energy per unit of mass. There are several flavors of nuclear propulsion being seriously considered. Nuclear thermal rockets heat a propellant like hydrogen using a fission reactor, achieving specific impulses roughly twice as good as chemical engines. NASA and various research institutions have been studying these designs for decades. In fact, The United States actually tested nuclear thermal engines back in the 1960s and early 70s under a program called NERVA. The technology worked. Political and budgetary pressures, not technical failures, ended the program. More recently, researchers have been exploring the centrifugal nuclear thermal rocket concept. This innovative design uses liquid nuclear fuel held in place by centrifugal force, potentially achieving specific impulses of around 1800 seconds. That's roughly double what conventional nuclear thermal rockets can manage. Studies published in 2025 suggest this technology could enable human missions to Mars with round-trip times of just 420 days and could potentially provide direct injection trajectories to the outer solar system and Kuiper Belt objects. But even these impressive nuclear systems aren't enough for true interstellar travel. They're stepping stones, crucial developments that will help us master deep space within our own solar system, but not quite powerful enough to bridge the gap between stars. For that, we need to think even bigger. We need to consider technologies that sound like they belong in science fiction, but are actually grounded in real physics. Enter the concept of fusion propulsion. While fission splits heavy atoms like uranium apart, fusion combines light atoms like hydrogen into heavier elements, releasing even more energy in the process. It's the same reaction that powers the Sun and every star in the universe. If we could harness controlled fusion for propulsion, we could theoretically achieve exhaust velocities of thousands of kilometers per second, potentially pushing spacecraft to significant fractions of the speed of light. Projects like the British Interplanetary Society's Project Daedalus in the 1970s and its successor Project Icarus have explored detailed designs for fusion-powered starships. The challenge, of course, is that we haven't yet achieved sustained controlled fusion here on Earth for power generation, let alone packaging it into a spacecraft. But progress is being made. Experimental fusion reactors are getting closer to break-even, the point where they produce more energy than they consume. Once we crack that puzzle for terrestrial power, adapting the technology for space propulsion becomes more realistic. Still, even fusion might not be our fastest path to the stars. There's another approach that has captured the imagination of scientists and billionaires alike, one that's already progressed from theory to actual laboratory testing. I'm talking about light sails and directed energy propulsion. Imagine a spacecraft with no fuel tanks, no engines, nothing but an enormous, incredibly thin, reflective sail. Now imagine pointing the most powerful laser array ever built directly at that sail, pushing it with pure photon pressure. This is the concept behind Breakthrough Starshot, a $100 million initiative announced in 2016 with backing from billionaire entrepreneur Yuri Milner and the late legendary physicist Stephen Hawking. The idea is elegantly simple in concept but fiendishly difficult in execution. You build a ground-based laser array capable of generating around 100 gigawatts of directed energy. That's roughly as much power as 100 nuclear reactors producing simultaneously. You aim this colossal beam at a tiny spacecraft called a Starship, equipped with a light sail just a few meters across but only hundreds of atoms thick. Under that intense photon bombardment, the sail accelerates at thousands of times Earth's gravity. Within minutes, it reaches 20% of the speed of light. That's about 60,000 kilometers per second. At that velocity, Proxima Centauri becomes reachable in roughly 20 years instead of tens of thousands. This isn't just theoretical dreaming anymore. In early 2026, researchers from Tuskegee University demonstrated a new photonic crystal light sail design that significantly improves efficiency over earlier concepts. The sail uses sophisticated metamaterials to better harness the momentum of incoming photons, bringing the entire Starshot concept closer to practical reality. And Breakthrough Starshot itself has completed its Phase 1 research, producing numerous scientific papers on everything from laser array engineering to metamaterial sail construction to the complex challenge of transmitting data back across light years of space. The work is solid, peer-reviewed and ongoing. Of course, enormous challenges remain. Building a 100-gigawatt laser array would be one of humanity's largest engineering projects ever undertaken. The light sails must survive intense acceleration and remain perfectly oriented. Communication across interstellar distances using tiny, gram-scale transmitters pushes the boundaries of what's physically possible. And then there's the question of what happens when your probe actually arrives at another star system, streaking past at 20% light speed with only seconds to gather data before the target world shrinks into the cosmic distance behind it. But here's what matters. For the first time in history, we have a plausible engineering pathway to interstellar travel within a human lifetime. Not centuries from now, not millennia, decades. Now, breakthrough Starshot focuses on sending tiny, robotic probes. But what about humans? What would it take to actually transport people to another star? This is where the challenge becomes truly staggering. A human crew needs life support, radiation shielding, living space, food, water, air recycling, medical facilities, and enough supplies to last the entire journey. We're not talking about a gram-scale chip anymore. We're talking about a vessel potentially massing thousands of tons. The faster you want to go, the more energy you need. And for human passengers, you can't accelerate at thousands of g-forces like a light sail probe. The human body maxes out at perhaps 3 to 5 Gs for sustained periods before serious medical problems develop. That means slower acceleration phases, longer journeys, and even more supplies. Let's consider some realistic scenarios. With advanced nuclear pulse propulsion, similar to the concepts explored in Project Orion back in the 1950s and 60s, a crewed starship might reach perhaps 5 to 10% of light speed. At that velocity, the journey to Proxima Centauri takes 40 to 80 years. That's a multi-generational voyage. The people who launch won't be the ones who arrive. Their grandchildren might be. Is that acceptable? Would you board a ship knowing you'd never reach the destination, but your descendants would? Throughout human history, countless pioneers have made similar sacrifices, leaving homelands they'd never see again, so their children could have better futures. Interstellar migration might simply be an extension of that ancient human drive. Alternatively, we could consider sleeper ships, put the crew into some form of suspended animation or hibernation, dramatically reducing their metabolic needs and essentially letting them skip through the decades of transit. This remains firmly in the realm of science fiction today, but researchers are making progress understanding the biological mechanisms behind natural hibernation in animals. Perhaps one day we'll unlock similar capabilities for humans, or we could build massive generation ships, essentially self-contained worlds carrying thousands of people who live out entire lives aboard the vessel. These would be arcs of humanity, preserving our species and culture across the void. The technical challenges are immense, from ecological life support systems that can function for centuries to social structures that can maintain stability across generations. But some researchers argue this might actually be more feasible than faster propulsion because it works with known physics and engineering rather than requiring breakthrough technologies. There's another option that occupies the far edge of physics but refuses to die in scientific discourse: the warp drive. You've probably heard of this concept from Star Trek, where the Enterprise bends space itself to travel faster than light without actually violating Einstein's cosmic speed limit. For decades, physicists dismissed this as pure fantasy. Then, in 1994, a Mexican theoretical physicist named Miguel Alcubierre did something remarkable. He showed mathematically that general relativity, Einstein's own masterwork, technically allows for such space-time distortions. The Alcubierre drive would contract space in front of a ship and expand it behind, creating a warp bubble that carries the vessel along at effectively superluminal speeds, while the ship itself never locally exceeds light speed. The catch? The original Alcubierre model required something called negative energy, or exotic matter, in quantities that would make the entire enterprise impossible. We don't even know if negative energy exists in usable forms, let alone how to produce or contain it. But science marches on. In December 2024, researchers announced a potentially groundbreaking paper proposing a fully physical model for warp drive that might not require exotic matter at all. The work is still highly theoretical and controversial. We're probably decades or centuries away from anything practical, if it's possible at all. But the fact that serious physicists are still finding new approaches to this problem tells us something important. We haven't hit the fundamental limits yet. The door remains cracked open. So let me bring all of this together and try to answer the central question. How long until humans achieve interstellar travel? The honest answer is that it depends on what you mean by achieve and what you mean by interstellar travel. If you mean sending a tiny robotic probe to another star system, we might accomplish this within the next 30 to 50 years. Breakthrough Starshot, or a similar directed energy mission, could theoretically launch by the 2040s or 2050s, arriving at Proxima Centauri by the 2060s or 2070s. You might live to see the first images from another star. If you mean sending humans to another star, we're looking at a much longer timeline. Conservative estimates suggest we might develop the necessary propulsion technology within 100 to 200 years. That puts human interstellar travel somewhere in the 22nd or 23rd century. Your great-great-grandchildren might be the first interstellar pioneers. If you mean practical, routine travel between star systems, something like hopping a flight between continents today, that's likely many centuries away, if it's possible at all. The energy requirements and engineering challenges are so immense that this might forever remain the province of desperate necessity rather than casual convenience. But here's what I want you to hold on to. Every single milestone in space exploration has come faster than the previous generation expected. When Konstantin Tsiolkovsky first proposed the rocket equation in 1897, putting a human on the moon seemed like madness. 72 years later, Neil Armstrong took that first step. When Einstein published general relativity in 1915, detecting gravitational waves seemed impossible. A century later, LIGO heard two black holes colliding a billion light-years away. We consistently underestimate what's possible when human ingenuity, resources, and determination align. Let's zoom out for a moment and think about this from a cosmic perspective. Because understanding where we stand in the universe's grand timeline might actually give us hope about where we're headed. The universe is approximately 13.8 billion years old. Our sun formed about 4.6 billion years ago. Life on Earth emerged roughly 3.8 billion years ago. But complex multicellular organisms only appeared around 600 million years ago. Dinosaurs ruled for 165 million years before an asteroid ended their reign 66 million years ago. Modern humans, Homo sapiens, have existed for merely 300,000 years. And technological civilization? The kind that builds radio telescopes and space probes? That's been around for barely a century. In cosmic terms, we're not just young, we're newborns. We've been a spacefaring species for less than 70 years. We've been seriously thinking about interstellar travel for maybe 50. The entire history of human technology, from the first stone tools to quantum computers, spans a mere eye blink compared to the age of the stars. So when someone asks, why haven't we reached the stars yet? The answer is simple: we've barely started trying. The fact that we're even having this conversation, that we can calculate trajectories to other solar systems and design theoretical starships, is remarkable. Our ancestors a few generations back couldn't have imagined any of this. Now let's talk about something that often gets overlooked in discussions of interstellar travel: the destinations themselves. Because it's not just about getting somewhere. It's about having somewhere worth going. For most of human history, we had no idea whether other stars even had planets. The assumption seemed reasonable, but proof remained elusive. Then in 1992, astronomers discovered the first confirmed exoplanets orbiting a pulsar, a rapidly spinning neutron star. 3 years later, in 1995, the first exoplanet around a Sun-like star was found, 51 Pegasi b, a scorching gas giant hugging its parent star in a tight 4-day orbit. Since then, the floodgates have opened. As of 2026, we've confirmed over 5,500 exoplanets, with thousands more candidates awaiting verification. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding by revealing that planets are extraordinarily common. On average, every star in our galaxy hosts at least one planet. Many have multiple worlds. And here's where things get truly exciting for interstellar ambitions. Some of these planets orbit within their star's habitable zone, the region where liquid water could potentially exist on a rocky surface. These are the worlds that might harbor life. These are the destinations that could one day become humanity's second homes. Proxima Centauri, our nearest stellar neighbor, hosts at least 3 confirmed planets. Proxima Centauri b is particularly tantalizing. It's a roughly Earth-mass world orbiting within the habitable zone, completing one orbit every 11.2 Earth days. The planet is tidally locked, meaning one side perpetually faces its star, while the other remains in eternal darkness. But the twilight zones between light and shadow might maintain temperatures suitable for liquid water. Could life exist there? We genuinely don't know. Proxima Centauri is a red dwarf star prone to violent flares that could strip away planetary atmospheres and sterilize surfaces. But life is remarkably adaptable. Underground ecosystems or ocean life beneath icy shells might survive such bombardment. The point is this: we now know that potentially habitable worlds exist right next door, astronomically speaking. The nearest one is just over 4 light-years away. That transforms interstellar travel from an abstract engineering challenge into a concrete scientific imperative. There's somewhere to go. There might be something or someone to find. Speaking of what we might find out there, I have to be honest with you about something. Interstellar travel isn't just about wonder and discovery. It also carries profound risks and terrifying realities that we need to confront. If you want to dive deeper into this darker side of cosmic exploration, I made a video called The Terrifying Truth About Interstellar Travel that explores the dangers in detail. The radiation exposure, the psychological challenges of decades in isolation, the possibility of arriving at a dead world or something far stranger than we imagined. I'd highly recommend watching it after this one. The link is in the description and on the card above. But for now, let's continue focusing on the question of when we might actually achieve this monumental goal. To understand our timeline, we need to examine the specific technologies under development and realistically assess how long each might take to mature. Let's start with what I call the near-term technologies, those we might see operational within the next 20 to 50 years. Solar sails have already been demonstrated in space. Japan's Icaros mission, launched in 2010, successfully deployed a solar sail and used sunlight pressure for propulsion. It was a proof of concept, not an interstellar vehicle, but it showed the fundamental physics works. The Planetary Society's Light Sail 2 mission further validated the technology in 2019. The next step involves scaling up dramatically and adding directed energy. Rather than relying on relatively gentle sunlight, we'd use powerful ground-based or space-based lasers to accelerate sails to much higher velocities. This is precisely what breakthrough Starshot aims to accomplish. The project completed its Phase 1 research successfully, with Jim Benford and other researchers documenting extensive findings on laser array design, sail materials, and mission architecture. A detailed book edited by Claude Phipps called Laser Propulsion in Space compiles much of this work, including fully worked-out examples by Kevin Parkin exploring how future voyages of humans traveling to stars might occur in large sailcraft over future centuries. The technical challenges are formidable but not impossible. Building a 100-gigawatt laser array would require massive infrastructure investment, comparable to major national projects like interstate highway systems or continental power grids. The sails must be fabricated from materials that don't exist yet, though metamaterial research is progressing rapidly. And the entire system must work with extraordinary precision, keeping a laser beam focused on a sail that quickly becomes millions of kilometers distant. Optimistic projections suggest a Starshot-type mission could launch by the late 2040s. More conservative estimates push this into the 2060s or beyond. Either way, we're talking about a time frame measured in decades, not centuries. That's revolutionary. Ion propulsion represents another technology making steady progress. Unlike chemical rockets that burn fuel in dramatic explosions, ion engines accelerate charged particles using electric fields. The thrust is tiny, mere fractions of a newton, but it's incredibly efficient and can operate continuously for years. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres, demonstrating the technology's ability to enable missions impossible with conventional rockets. The European Space Agency's Smart 1 mission to the Moon also relied on ion engines. For interstellar travel, ion propulsion alone won't suffice. The velocities achieved are still far too slow, but combined with nuclear power sources, ion engines could enable fast transit through our outer solar system, serving as testbeds for the technologies and operational experience we'll need for eventual interstellar missions. A particularly ambitious concept involves using the Sun itself as a gravitational slingshot. By diving close to our star and firing engines at the perihelion, spacecraft can gain enormous velocity boosts, potentially achieving speeds of 100 kilometers per second or more. This technique, sometimes called an Oberth maneuver, could dramatically reduce transit times to the outer solar system and beyond. Research published in early 2026 by Slava Turishev at NASA's Jet Propulsion Laboratory explores mission concepts to reach the solar gravitational lens focal region, roughly 650 to 900 astronomical units from the Sun. At that distance, the Sun's gravity bends light from distant objects, potentially enabling us to directly image exoplanets with extraordinary resolution. Reaching this region in 20 years requires velocities around 154 kilometers per second, pushing the boundaries of near-term propulsion technology. The study examined several approaches: advanced solar sails with extremely low mass that could survive close solar passes, nuclear electric propulsion systems, and hybrid architectures combining multiple technologies. Each pathway has specific requirements and technology readiness milestones that would need to be achieved by the early 2030s for a credible launch window between 2035 and 2040. This isn't interstellar travel yet, but it's a crucial stepping stone. Mastering rapid transit to several hundred astronomical units teaches us how to operate spacecraft at enormous distances with minimal communication delays. It builds the infrastructure and expertise for eventual missions to other stars. Nuclear propulsion, as I mentioned earlier, represents perhaps our most realistic path to dramatically faster space travel in the coming decades. The technology has a fascinating and somewhat tragic history. Back in the 1960s, the United States pursued nuclear thermal rockets under Project Rover and the NERVA program. Engineers successfully tested multiple nuclear rocket engines, demonstrating that the technology worked. A NERVA engine could achieve roughly twice the efficiency of the best chemical rockets, opening possibilities for crewed missions to Mars and beyond. Then politics intervened. Budget cuts in the early 1970s killed the program before it could fly in space. Decades of potential progress vanished. We've been playing catch-up ever since. Now, interest is reviving. NASA and the Defense Advanced Research Projects Agency, DARPA, are collaborating on the Demonstration Rocket for Agile Cislunar Operations, or DRACO program. The goal is to demonstrate a nuclear thermal propulsion system in space by 2027 or 2028. If successful, this could revolutionize human exploration of the solar system. Beyond nuclear thermal propulsion lies nuclear pulse propulsion, the concept explored by Project Orion in the 1950s and 60s. The idea sounds almost absurd. Detonate nuclear bombs behind a spacecraft riding the explosion's shockwave on a massive pusher plate. Yet the physics is sound. Freeman Dyson, one of the 20th century's greatest physicists, worked on the project and remained convinced throughout his life that it could work. A nuclear pulse vehicle could theoretically achieve exhaust velocities of perhaps 3 to 5% of light speed, potentially reaching Proxima Centauri in about a century. That's still a multi-generational journey, but it's vastly better than the tens of thousands of years required by chemical rockets. The obvious problems involve politics and environmental concerns. Detonating nuclear weapons in Earth's atmosphere, or even in low orbit, is prohibited by the Partial Nuclear Test Ban Treaty of 1963. Any nuclear pulse vehicle would need to be launched conventionally and only begin its nuclear detonation sequence once safely in deep space. The international legal and diplomatic challenges are immense. Still, in a future where climate change, asteroid impacts, or other existential threats make interstellar migration a matter of survival rather than curiosity, these objections might fade. When the stakes are high enough, humanity tends to find ways around obstacles. Let's discuss fusion propulsion in more depth, because this technology might represent the sweet spot between near-term feasibility and interstellar capability. Fusion, the process that powers the Sun, releases energy by combining light atomic nuclei into heavier ones. When hydrogen isotopes like deuterium and tritium fuse into helium, they release enormous energy. A single gram of fusion fuel contains as much energy as several tons of chemical rocket propellant. For decades, controlled fusion has remained tantalizingly just out of reach, prompting the old joke that fusion power is always 30 years away. But real progress is happening. The ITER project in France, the largest fusion experiment ever built, aims to demonstrate net energy gain by the early 2030s. Private companies like Commonwealth Fusion Systems and TAE Technologies are pursuing alternative approaches that might achieve results even sooner. Once we crack fusion for terrestrial power generation, adapting it for spacecraft propulsion becomes more tractable. A fusion rocket could theoretically achieve exhaust velocities of several hundred to over 1,000 kilometers per second, potentially pushing spacecraft to 5 or even 10% of light speed. Project Daedalus, a study conducted by the British Interplanetary Society between 1973 and 1978, designed a detailed fusion-powered starship capable of reaching Barnard's star, about 6 light-years away, within 50 years. The vehicle would have been massive, over 50,000 tons at launch, using pellets of deuterium and helium-3 ignited by electron beams. It remains one of the most thoroughly engineered interstellar vehicle concepts ever produced. The successor study, Project Icarus, launched in 2009, revisited these concepts with updated physics and technology. Researchers explored alternative fusion approaches, different target stars, and various mission profiles. The work continues today through organizations like the Initiative for Interstellar Studies. Realistically, a fusion-powered interstellar probe probably won't fly for at least 50 to 100 years. We first need to master fusion power generation, then miniaturize and harden the technology for spacecraft applications, then build and test prototypes in deep space environments. Each step takes decades, but here's the inspiring part. The path is clear. We know the physics works. We understand the engineering challenges. It's not a matter of discovering new science, but of developing existing science into practical technology. That's a solvable problem given enough time, resources, and determination. Now, I want to address something that often gets lost in technical discussions of interstellar travel, the human element. Because ultimately, this isn't just about rockets and physics. It's about who we are as a species and what we're capable of becoming. Look at what we've accomplished in the last century. In 1926, exactly 100 years ago from when you're watching this, Robert Goddard launched the first liquid-fueled rocket. It flew for 2.5 seconds and reached an altitude of 12 meters. Just 43 years later, humans walked on the moon. Another 57 years after that, we have robots on Mars, spacecraft orbiting Jupiter and Saturn, and probes that have left the solar system entirely. Voyager 1, launched in 1977, is currently over 24 billion kilometers from Earth, the most distant human-made object in existence. It's traveling at about 17 kilometers per second relative to the Sun. At that speed, reaching Proxima Centauri would take over 70,000 years. But Voyager was never designed for interstellar travel. It was built with 1970s technology for a grand tour of the outer planets. The fact that it's still functioning and still sending data nearly 5 decades later is a testament to engineering excellence, but it doesn't represent our best possible effort at crossing interstellar distances. When humanity truly commits to reaching the stars with the full weight of our technological capability and economic resources, we'll do far better than Voyager. How much better? That depends on choices we haven't yet made. This brings me to perhaps the most important factor in determining our interstellar timeline: motivation. Throughout history, great explorations have required compelling reasons. The European voyages of discovery were driven by the desire for trade routes, resources, and territorial expansion. The Apollo program was propelled by Cold War competition with the Soviet Union. Without strong motivations, even technically feasible projects never materialize. What might motivate humanity to actually build interstellar spacecraft? Scientific curiosity is powerful, but historically insufficient for mobilizing the enormous resources required. We care about understanding the cosmos, but not usually enough to spend trillions of dollars pursuing it. National prestige, the force behind Apollo, could return. If one nation or bloc announces serious interstellar intentions, others might follow to avoid being left behind. A new space race, this time aimed at the stars, could accelerate development dramatically. Economic incentives seem unlikely for early interstellar missions. There's nothing at Proxima Centauri that we can't obtain more easily closer to home. Perhaps in the far future, if we discover valuable resources or habitable worlds, economic motivations might emerge. But for pioneering missions, other drivers will be needed. Survival instincts might ultimately prove the strongest motivation. If humanity faces existential threats, whether from climate collapse, asteroid impact, supervolcanic eruptions, engineered pandemics, or artificial intelligence gone wrong, dispersing to multiple star systems becomes a survival strategy. You don't keep all your eggs in one basket. The philosopher Nick Bostrom has written extensively about existential risk, and many serious thinkers now argue that becoming a multiplanetary and eventually multistellar species is essential for long-term human survival. Elon Musk has cited similar reasoning for his Mars colonization ambitions. If this perspective gains wider acceptance, if humanity collectively recognizes that our long-term existence depends on spreading beyond Earth and eventually beyond the solar system, then the resources and willpower for interstellar travel might materialize faster than purely technical projections suggest. Let's talk about something that fundamentally shapes our interstellar timeline: the sheer economics of reaching the stars. Building an interstellar spacecraft isn't like building an airplane or even a space shuttle. We're talking about engineering projects that would dwarf anything humanity has ever attempted. The costs involved are so enormous that they force us to think differently about how civilization organizes itself. Consider breakthrough Starshot's laser array concept. To accelerate a gram-scale probe to 20% of light speed requires roughly 100 gigawatts of power delivered in a matter of minutes. Building the laser infrastructure alone would cost tens of billions of dollars, possibly hundreds of billions, when you factor in the power generation systems, cooling mechanisms, adaptive optics, and control systems required. And that's for a tiny probe weighing less than a paperclip. Scale up to something capable of carrying scientific instruments with meaningful capability, and costs multiply. Scale up further to something capable of carrying humans, and you're looking at expenditures that would strain the entire global economy. For perspective, the Apollo program cost approximately $25 billion in 1960s money, equivalent to roughly $260 billion in today's currency. That represented about 2.5% of the United States federal budget at its peak. The International Space Station has cost over $150 billion across all partner nations over its lifetime. An interstellar mission capable of reaching another star within a human lifetime might cost trillions of dollars, perhaps tens of trillions. Nobody knows for certain because we've never priced out such an endeavor in detail. This doesn't mean it's impossible. Global GDP currently exceeds $100 trillion annually. Humanity absolutely possesses the economic capacity to fund interstellar missions if we chose to prioritize them. The question is whether we will make that choice and when. Here's where long-term thinking becomes crucial. Individual nations, even wealthy ones, might struggle to justify such expenses alone. But humanity as a whole, working across generations, could absolutely accomplish this. Consider how we've built other monumental projects throughout history. The Great Wall of China was constructed over centuries by successive dynasties. Medieval cathedrals often took 100 years or more to complete, with workers who laid the foundations never seeing the finished spires. The interstate highway system in the United States took 35 years to build and cost nearly $530 billion in today's dollars. Interstellar travel might require similar multi-generational commitment. Perhaps we begin with robotic probes in the mid-21st century, establish permanent bases throughout our solar system by the late 21st century, develop fusion propulsion in the 22nd century, and launch our first crewed interstellar missions in the 23rd century. Each generation builds upon the previous one's work, slowly but steadily extending humanity's reach toward the stars. This perspective actually makes the whole endeavor feel more achievable, not less. We don't need miraculous breakthroughs happening all at once. We need steady progress sustained over time, and that's something humans are remarkably good at when we set our minds to it. There's another economic factor worth considering: the decreasing cost of technology over time. In 1969, the Apollo guidance computer that helped land humans on the Moon had roughly 74 kilobytes of memory and operated at about 0.04 megahertz. It cost millions of dollars to develop. Today, a basic smartphone is millions of times more powerful and costs a few $100s. Similar cost reductions have occurred across virtually every technology domain. Solar panels that cost $76 per watt in 1977 now cost less than 30 cents per watt. Genome sequencing that cost nearly $3 billion for the Human Genome Project can now be done for a few $100s. Satellite launches that once cost tens of thousands of dollars per kilogram are dropping toward hundreds of dollars as reusable rockets mature. If these trends continue, technologies that seem prohibitively expensive today might become affordable within decades. The laser arrays needed for directed energy propulsion might benefit from advances in photonics and manufacturing. The lightweight materials needed for solar sails might emerge from nanotechnology breakthroughs. The computing power needed to navigate interstellar distances might ride the ongoing wave of semiconductor improvements. None of this is guaranteed. Technological progress can stall, reverse, or take unexpected directions. But the historical trend strongly suggests that what seems impossibly expensive today often becomes routine tomorrow. Now let's examine some specific mission concepts that researchers are actively studying. These aren't science fiction fantasies, but serious engineering proposals backed by detailed analysis. The Solar Gravitational Lens mission I mentioned earlier represents one of the most exciting near-term possibilities. By traveling to around 650 astronomical units from the Sun, a spacecraft could use our star's gravitational field as a natural telescope of almost unimaginable power. At that distance, the Sun's gravity bends light from distant objects, focusing it in ways that would allow us to image exoplanets not as single points of light, but as resolved disks with visible surface features. We could potentially see continents, oceans, and cloud patterns on worlds orbiting other stars. We could detect atmospheric compositions that might reveal signs of life. This isn't interstellar travel in the sense of visiting another star, but it achieves one of interstellar travel's primary goals, learning about other worlds in extraordinary detail. And it's potentially achievable with technology we could develop within the next 15 to 20 years. The mission requirements are demanding, but not impossible. You need a spacecraft capable of reaching 650 astronomical units in roughly 20 years, which means achieving velocities around 150 kilometers per second. Current chemical rockets can't come close to this, but advanced solar sails diving close to the Sun, nuclear electric propulsion systems, or hybrid architectures combining multiple technologies might achieve these speeds. Slava Turishev's 2026 analysis identifies specific technology demonstrations needed by the early 2030s for a credible launch window between 2035 and 2040. We're talking about real mission planning with concrete milestones, not vague aspirations for some indefinite future. Another fascinating concept involves using the Sun itself for propulsion through what's called a sun diver maneuver. Here's how it works. A spacecraft equipped with a highly reflective, heat-resistant sail approaches the Sun extremely closely, perhaps within 10 to 20 solar radii of the surface. At that proximity, solar radiation pressure becomes enormous. The sail deploys, catching photons like wind, filling a ship's canvas, and the spacecraft accelerates outward at tremendous velocity. The closer you can get to the Sun, the more speed you gain, but survival becomes increasingly challenging. At 10 solar radii, temperatures exceed 1,000 degrees Celsius. The sail material must reflect nearly all incoming radiation while remaining structurally intact under intense stress. Recent advances in high-temperature materials, including refractory metals and advanced ceramics, are making such missions more feasible. Some researchers estimate that a well-designed sundiver sail could achieve exit velocities of 100 to 150 kilometers per second, enough to reach the outer solar system in years rather than decades. This technology serves as a stepping stone toward true interstellar missions. Master the sundiver maneuver, and you've demonstrated key capabilities needed for more ambitious journeys. Let's shift our attention to propulsion concepts that remain more speculative but could potentially revolutionize interstellar travel if they prove feasible. Antimatter propulsion represents the ultimate in energy density. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation E equals mc squared. Compare this to nuclear fission, which converts less than 1% of mass to energy, or fusion, which converts less than 1% as well. Antimatter is roughly 100 times more efficient than the best nuclear reactions. A spacecraft powered by antimatter annihilation could theoretically achieve velocities approaching significant fractions of light speed. Some calculations suggest that an antimatter rocket could reach 40% of light speed or even higher, potentially reducing transit times to Proxima Centauri to just a decade or so. The catch, and it's an enormous catch, is that we currently have no way to produce or store antimatter in useful quantities. The total amount of antimatter ever created by all of humanity's particle accelerators combined amounts to mere nanograms. Producing a single gram would require more energy than the entire world generates in a year. And storing antimatter is equally challenging since it annihilates instantly upon contact with ordinary matter. Some researchers are exploring concepts for antimatter harvesting. The Earth's magnetic field actually traps small quantities of antimatter produced by cosmic ray interactions. In principle, a spacecraft could collect this naturally occurring antimatter over time. But the amounts are tiny and the collection systems would need to be enormous. For now, antimatter propulsion remains firmly in the theoretical category. It might become practical in a century or two if we develop dramatically more efficient production methods. Or it might forever remain impractical, a tantalizing possibility that physics allows but engineering can never achieve economically. There's another propulsion concept that sounds even more fantastical, but is being taken increasingly seriously by physicists, using the quantum vacuum itself for propulsion. Space, even the emptiest vacuum, isn't truly empty. According to quantum field theory, virtual particles constantly pop in and out of existence everywhere in the universe. This quantum foam represents energy inherent to space-time itself, sometimes called zero-point energy. Could we somehow harness this vacuum energy for propulsion? The idea sounds like perpetual motion, something that violates fundamental physics, and indeed, most physicists remain deeply skeptical. But some researchers continue exploring the possibility. Concepts like the quantum vacuum plasma thruster and various zero-point energy extraction schemes occasionally appear in scientific literature. None have been experimentally verified. Most physicists expect they never will be. Still, the history of physics teaches humility. Phenomena once considered impossible, like quantum entanglement or the Casimir effect, turned out to be real. We shouldn't dismiss ideas simply because they seem strange. For our interstellar timeline, these exotic propulsion concepts probably don't matter much. Even if theoretically possible, they're so far from practical realization that they won't affect when humanity reaches the stars. But they remind us that physics may still contain surprises that could transform everything. Let me introduce you to a concept that might actually shorten our effective journey times without requiring faster propulsion: the interstellar highway system. Imagine this scenario: humanity launches its first interstellar probe toward Proxima Centauri around 2050. The tiny craft, powered by directed energy, reaches 20% of light speed and arrives around 2070. It surveys the system and sends back data. Based on what we learn, we decide to send a larger follow-up mission. This one launches around 2075 with improved technology, reaching perhaps 25% of light speed. It arrives around 2092, but here's where it gets interesting. Along the way, both missions have deposited small relay stations at intervals of 1 or 2 light years. These relays boost communication signals, allowing faster and more reliable data transmission. They also serve as navigation beacons for subsequent missions. Now imagine extending this pattern. Over the next few centuries, humanity establishes a network of outposts stretching from our solar system toward nearby stars. Each generation builds upon previous infrastructure. Propulsion technology continues improving. Journey times keep shrinking. By the 23rd or 24th century, what started as isolated pioneering missions has evolved into something resembling a transportation network. Not quick or easy by any means, but systematic and sustainable. This vision suggests that interstellar travel might not arrive as a single dramatic breakthrough, but as a gradual expansion, each step making the next one easier. There's profound philosophical importance in this journey toward the stars that extends far beyond engineering specifications and timeline estimates. Throughout human existence, we've defined ourselves partly by our relationship with the unknown. We're explorers by nature. Every continent, every ocean, every mountain range has eventually drawn human footsteps. We simply cannot resist the call of distant horizons. The stars represent the ultimate horizon. They've captivated human imagination since our ancestors first looked up and wondered what those points of light might be. Ancient cultures wove the stars into their mythologies, their navigation systems, their calendars. Modern science has revealed them to be other suns, many hosting their own planetary systems, potentially their own life forms. To reach the stars would be the culmination of our species' deepest drives. It would transform us from a planetary species confined to a single, fragile world into something far grander, a cosmic civilization with presence across light years. This isn't just about survival, though survival matters. It's about meaning. It's about becoming who we have the potential to become. The question isn't just how energy represents perhaps the single greatest obstacle to interstellar travel. Everything else, navigation, communication, propulsion, life support, ultimately depends on having sufficient energy available. Let's put the energy requirements into perspective. Accelerating a 1 kilogram spacecraft to 20% of light speed requires approximately 1.8 petajoules of energy. That's roughly equivalent to the energy released by a medium-sized nuclear weapon for a single kilogram. Scale up to a 1-ton probe with scientific instruments, and you need 1.8 exajoules. That's approximately the total energy consumption of the entire United States for about 2 weeks. Scale up further to a crewed vessel of perhaps 10,000 tons, a minimal estimate for a self-sustaining interstellar arc, and the energy requirements become almost incomprehensible. We're talking about the total energy output of human civilization for years, perhaps decades, concentrated into propelling a single spacecraft. Where does this energy come from? How do we generate, store, and deploy it? For directed energy approaches like breakthrough Starshot, the energy comes from ground-based infrastructure. Massive solar farms or nuclear plants generate electricity that powers the laser array. The spacecraft itself doesn't carry the energy, it receives it as photon pressure. This is why Starshot focuses on tiny, gram-scale probes. The energy requirements scale with mass, so minimizing mass makes the whole concept feasible. For self-propelled spacecraft carrying their own fuel, the challenge intensifies dramatically. Chemical fuels are far too weak. Nuclear fission offers better energy density but still falls short for relativistic velocities. Fusion improves things further but remains technologically immature. Antimatter represents the theoretical maximum but remains practically unattainable. Some researchers have proposed collecting energy en route. Interstellar ramjets would scoop up hydrogen from the diffuse interstellar medium and use it as fusion fuel. The concept is elegant, unlimited range without carrying fuel. Unfortunately, detailed analysis reveals serious problems. The interstellar medium is so sparse that the magnetic scoop required to collect sufficient hydrogen would create more drag than the fusion engine could overcome. The physics doesn't work with any known materials or designs. Other concepts involve beamed power throughout the journey. Rather than one big push at the beginning, a network of relay stations could continuously power the spacecraft with laser or microwave energy. This distributes the infrastructure requirements but multiplies the engineering complexity. No perfect solution exists yet. Energy remains the hard wall that all interstellar concepts eventually slam against. Material science represents another frontier where breakthroughs could dramatically accelerate our interstellar timeline. Consider the requirements for a solar sail that must survive passing close to the Sun. The material must reflect nearly all incoming radiation to prevent overheating. It must remain mechanically stable at temperatures exceeding 1000 degrees Celsius. It must be incredibly thin to minimize mass while covering enormous areas, and it must maintain precise shape under the stress of photon pressure. No existing material satisfies all these requirements perfectly. Researchers are exploring advanced options including graphene-based composites, metamaterials with engineered optical properties, and thin films of refractory metals. Each has advantages and drawbacks. Progress is steady but slow. For nuclear or fusion propulsion, materials must withstand extreme radiation environments for decades without degradation. Reactor components face neutron bombardment that literally knocks atoms out of their crystal structures, causing embrittlement and eventual failure. Developing materials that can survive decades of such punishment while remaining lightweight enough for spacecraft applications is a formidable challenge. For any long-duration mission, even without extreme temperatures or radiation, materials must resist degradation from cosmic rays, micrometeorite impacts, and simple aging. Plastics become brittle, metals corrode, electronics fail. A century-long journey demands materials with century-long lifespans in the harshest environment imaginable. The good news is that materials science is advancing rapidly. Nanotechnology allows us to engineer materials at the atomic level, creating structures with properties impossible in natural substances. Computational materials science lets us simulate millions of potential compounds before synthesizing the most promising candidates. The pace of discovery is accelerating. Still, translating laboratory breakthroughs into spacecraft-ready components takes decades. A material invented today might not fly on an interstellar mission for 30 or 40 years after it's been characterized, tested, qualified, and incorporated into mature designs. Let me now address the biological challenges of interstellar travel, because sending humans rather than robots adds enormous complexity. The human body evolved for conditions on Earth's surface: standard gravity, protection from radiation by atmosphere and magnetic field, abundant oxygen, moderate temperatures, and social connection with other humans. An interstellar spacecraft must recreate or substitute for all these requirements. Radiation poses one of the most serious threats. Beyond Earth's protective magnetosphere, astronauts face continuous bombardment from galactic cosmic rays, high-energy particles accelerated by distant supernovae, and other violent astrophysical events. These particles penetrate typical spacecraft hulls and can damage DNA, increasing cancer risk and potentially causing neurological problems. For a journey lasting decades or centuries, cumulative radiation exposure becomes severe. Potential solutions include massive shielding, which dramatically increases spacecraft mass, or active magnetic shielding, which requires enormous power. Neither approach has been demonstrated at scale. Microgravity presents another challenge. Extended weightlessness causes bone loss, muscle atrophy, cardiovascular deconditioning, and vision problems. Astronauts on the International Space Station exercise extensively to minimize these effects, but missions lasting months still produce significant physiological changes. A journey lasting decades would likely cause irreversible damage. The solution is artificial gravity, most practically achieved through rotation. A rotating spacecraft creates centrifugal force that simulates gravity, but the rotation rate and radius must be carefully balanced. Too fast, and passengers experience disorienting Coriolis effects. Too small, and the gravity gradient between head and feet causes discomfort. Practical artificial gravity systems require large structures, again increasing mass. Psychological challenges might prove even more daunting than physical ones. Humans are social creatures who need varied experiences, new stimuli, and meaningful connections. An interstellar journey confines travelers to a tiny artificial environment for periods exceeding human lifespans. How do you maintain mental health under such conditions? The psychological research on isolated environments, from Antarctic stations to submarine deployments to space missions, suggests that careful crew selection, meaningful work, and connection with loved ones help maintain well-being. But no one has ever experienced isolation on interstellar timescales. We're extrapolating from weeks and months to decades and centuries. The psychological unknowns are vast. These biological challenges point toward a provocative possibility. Perhaps the first humans to reach another star won't be biological humans at all. Advances in artificial intelligence and robotics might eventually produce machines that match or exceed human cognitive capabilities. Such artificial minds wouldn't suffer from radiation damage, wouldn't need gravity, wouldn't experience psychological distress from isolation, and could potentially operate for centuries without biological maintenance. Uploading human consciousness into artificial substrates, sometimes called mind uploading, represents an even more speculative possibility. If we could transfer the patterns of a human brain into a computer, that digital person could theoretically travel to the stars without biological limitations. They would experience the journey, make decisions, feel curiosity and wonder, but without fragile flesh constraining their possibilities. These concepts raise profound philosophical questions. Is a digital copy of a person really that person? Would an artificial intelligence, even one derived from human brain scans, possess genuine consciousness? Or would we be sending sophisticated but ultimately empty machines to worlds that deserve to be experienced by truly sentient beings? I don't have answers to these questions. Nobody does. But they might become practically relevant before biological humans ever cross interstellar distances. Our robotic emissaries might precede us by centuries, and some of those robots might carry something resembling human minds. Let's return to more concrete considerations and examine some specific mission architectures being studied for interstellar travel. The world ship or generation ship concept envisions a massive, self-sustaining vessel carrying thousands of people on a journey lasting centuries. The original crew would die during transit. Their descendants would arrive at the destination. The ship itself becomes a miniature world, complete with ecosystems, agriculture, industry, and social structures. This approach has certain advantages. It doesn't require propulsion breakthroughs beyond what nuclear pulse or advanced fusion might provide. The technologies for closed-loop life support, while challenging, seem more tractable than relativistic propulsion. And humans have experience building complex social structures that persist across generations. But the challenges are immense. A world ship would need to mass millions of tons to support a viable population with sufficient genetic diversity. It would need ecological systems that remain stable for centuries without external inputs. It would need governance structures that maintain social cohesion across dozens of generations born knowing nothing but the ship's interior. Could such a society maintain purpose and motivation? The founders chose to embark on this journey, but their descendants had no say. Would people born on the ship embrace their ancestors' mission, or would they resent being condemned to lives in a metal box hurtling through darkness? Sociologists and psychologists have barely begun exploring these questions. Some researchers suggest starting with smaller, faster ships that could reach nearby stars within a single, long human lifetime. If we could achieve 15 or 20% of light speed, the journey to Proxima Centauri shrinks to around 25 to 30 years. People who board in their 20s might arrive in their 50s, old but still alive. This approach requires either breakthrough propulsion or accepting that only a select few will make the journey during their biologically active years. Suspended animation, if we could develop it, might allow passengers to skip the boring decades of transit. Speaking of suspended animation, this concept deserves deeper exploration because it could fundamentally change interstellar mission design. Nature provides existence proofs that biological systems can be dramatically slowed. Some animals enter states of hibernation or torpor, where metabolic rates drop to a fraction of normal. Tardigrades can survive in cryptobiosis for decades, appearing dead but reviving when conditions improve. Certain frogs survive being frozen solid through winter. Could humans enter similar states? Research is ongoing but preliminary. Some medical procedures already induce hypothermia to slow metabolism during surgeries. Experiments with induced torpor in pigs and other animals show promise, but we're far from being able to put a human into suspended animation for years or decades, let alone centuries. The challenges include preventing cellular damage from prolonged stasis, maintaining brain function without cognitive degradation, and safely reviving subjects after extended periods. Each presents formidable biological hurdles. If we could crack suspended animation, interstellar missions become dramatically more feasible. Crew members could sleep through most of the journey, requiring minimal life support resources. Psychological stress from isolation becomes irrelevant if you're unconscious. A ship designed for sleeping passengers could be far smaller and lighter than a generation ship designed for living communities. Some researchers estimate that practical human suspended animation might be developed within 50 to 100 years. If so, it could arrive just in time to enable the first crewed interstellar missions. Here's an interesting question that affects our timeline estimates. How fast does progress actually happen in aerospace technology? Looking at historical patterns might help us project forward. Powered flight began in 1903 with the Wright brothers' 12-second hop. Just 66 years later, humans walked on the moon. That's remarkable progress from wood and fabric biplanes to Saturn V rockets within a single human lifetime. But then something interesting happened. After Apollo, progress in human spaceflight slowed dramatically. The space shuttle, while impressive, didn't fundamentally advance our capabilities beyond low Earth orbit. The International Space Station has operated for over 2 decades, but hasn't extended human presence further into space. No human has traveled beyond low Earth orbit since 1972. What explains this deceleration? Several factors contributed. The Cold War space race that drove Apollo funding ended. Public interest waned once the moon was conquered. Budgets shifted to other priorities. The physics of spaceflight are genuinely hard, and early rapid progress harvested the low-hanging fruit. Will progress toward interstellar travel follow a similar pattern? An initial burst of enthusiasm and rapid advancement followed by decades of stagnation? Or will different dynamics apply? I suspect we're approaching an inflection point. Multiple factors are converging that could accelerate space development: reduced launch costs from reusable rockets, growing private sector investment, international competition, especially from China, increasing awareness of existential risks, and the sheer accumulation of technological capability across many relevant fields. The next 50 years might see more progress than the previous 50, and if that happens, our interstellar timeline might be shorter than historical extrapolations suggest. Another factor that could accelerate our timeline involves the search for extraterrestrial intelligence, commonly known as SETI. For over 60 years, scientists have been scanning the skies for signals from alien civilizations. So far, we've detected nothing conclusive, but the search continues with increasingly sophisticated instruments and analysis techniques. What if we detected an unambiguous artificial signal from another star system? The impact on human society would be profound and difficult to predict. But one likely consequence would be dramatically increased interest in actually traveling to the signal's source. Consider the scenario. Astronomers announced detection of clearly technological signals from a planet orbiting, say, Tau Ceti, roughly 12 light-years away. The signals indicate an active civilization, perhaps one attempting to communicate with us. Suddenly, interstellar travel transforms from abstract ambition to concrete imperative. We'd want to respond, to learn more, perhaps eventually to meet these beings. The resources that might flow toward interstellar capability following such a discovery could dwarf anything previously invested. National pride, scientific curiosity, security concerns, religious implications, all would combine to make reaching other stars a civilizational priority. Of course, this scenario might never occur. Perhaps we're alone in the galaxy, perhaps other civilizations exist but are too distant to detect. Perhaps they're deliberately hiding, we simply don't know. But the possibility of detection adds an element of unpredictability to our timeline estimates. A single announcement tomorrow morning could transform interstellar travel from a distant dream to an urgent necessity. Let me share another perspective that might reshape how you think about this question. We've been discussing interstellar travel as something humanity will eventually achieve. But perhaps we should consider whether it's something humanity must achieve, not just for exploration or survival, but for moral reasons. If life is rare in the universe, if our little planet hosts something cosmically precious, then spreading that life to other stars becomes almost a duty. We'd be the custodians of something irreplaceable, obligated to protect and propagate it. Even if life exists elsewhere, our particular form of life, with our consciousness, our culture, our capacity for wonder and creation, might be unique. The universe might produce intelligence repeatedly across billions of galaxies, but it would never produce another humanity. Our stories, our music, our science, our love, these would be lost forever if we remained confined to Earth, and something eventually destroyed us. This argument suggests that interstellar travel isn't just an option to consider, but a responsibility to fulfill. Every generation that fails to advance toward the stars is failing a duty to the future. I find this perspective both inspiring and unsettling. It raises the stakes enormously. It suggests that our current complacency about interstellar travel might be not just short-sighted, but morally negligent. You might disagree. Perhaps you think humanity has no cosmic obligation beyond our own flourishing. Perhaps you think the resources required for interstellar travel could better address immediate problems here on Earth. These are valid perspectives that deserve consideration, but I suspect that future generations looking back at us from habitats orbiting distant stars will judge our era by what we did to extend humanity's reach beyond this single, vulnerable world. Let's dive into something that often gets overlooked in discussions about interstellar travel, the destination selection problem. Because it's not enough to develop the technology to reach another star. We also need to figure out which star to visit and why. Within about 15 light-years of our Sun, there are approximately 50 stellar systems containing around 70 individual stars. Some are binary or triple star systems. Some are tiny red dwarfs barely visible even to powerful telescopes. Some are Sun-like stars that might host Earth-like planets. Proxima Centauri gets most of the attention because it's closest, sitting just 4.24 light-years away. But closest doesn't necessarily mean best. Proxima is a flare star, prone to violent outbursts that could sterilize any planets in its habitable zone. Its confirmed planet, Proxima Centauri b, might be a dead world bathed in lethal radiation. Alpha Centauri A and B, the binary pair that Proxima orbits, offer more Sun-like conditions. Alpha Centauri A is slightly larger and brighter than our Sun. Alpha Centauri b is slightly smaller and dimmer. Both could potentially host habitable planets, though none have been confirmed yet. The system lies about 4.37 light-years away, marginally farther than Proxima, but still our nearest substantial stellar neighbors. Barnard's star, a red dwarf about 6 light-years away, hosts at least one confirmed planet. The star is ancient, perhaps twice the age of our Sun, and relatively quiescent compared to Proxima. It was the original target for Project Daedalus, the British Interplanetary Society's fusion starship study from the 1970s. Tau Ceti, a Sun-like star roughly 12 light-years distant, shows tantalizing hints of multiple planets, including some in the habitable zone. Its similarity to our Sun makes it an attractive destination despite the greater distance. Epsilon Eridani, about 10.5 light-years away, hosts a confirmed giant planet and possibly additional smaller worlds. At less than 1 billion years old, it's a young system that might give us insight into how planetary systems form and evolve. Each potential destination offers different scientific rewards and poses different challenges. A comprehensive interstellar program might eventually send missions to all nearby stars. But for the first mission, destination selection requires careful consideration of multiple factors: distance, travel time, scientific interest, probability of finding habitable worlds, and probability of finding life. The question of what we're looking for profoundly shapes mission design. Are we seeking worlds to colonize, signs of extraterrestrial life, pure scientific knowledge? Each objective implies different target selection criteria and different spacecraft capabilities. If colonization is the goal, we need planets with conditions humans can tolerate, at least with technological assistance. That means rocky planets in habitable zones, ideally with breathable atmospheres or at least resources to create them. Such worlds appear to be relatively common based on exoplanet surveys, but we don't yet know which nearby stars host them. If finding life is the goal, the criteria shift somewhat. Life might exist on worlds inhospitable to human colonization, beneath icy moons with subsurface oceans, in the upper atmospheres of gas giants, or in environments we haven't even imagined. The most scientifically interesting destination might not be the most hospitable. If pure scientific return is the priority, we might favor targets that teach us the most about planetary formation, stellar evolution, or fundamental physics, regardless of habitability. Young systems show us how planets form. Old systems show us how they age. Binary systems reveal dynamics impossible in our single-star environment. Realistically, first missions will probably pursue multiple objectives simultaneously. A probe visiting Proxima Centauri would study the star itself, characterize all planets in the system, search for biosignatures, assess colonization potential, and gather data on the interstellar medium it traversed. No scientific opportunity would be wasted after such an enormous investment. Here's something fascinating to consider. By the time our first interstellar probes launch, we might already have detailed knowledge of their destinations from Earth-based observations. Astronomy is advancing rapidly. The James Webb Space Telescope, launched in 2021, can analyze exoplanet atmospheres in unprecedented detail. Future telescopes will push these capabilities further. The European Extremely Large Telescope, with a primary mirror 39 meters across, will enable direct imaging of some nearby exoplanets. Space-based interferometers could potentially resolve surface features on worlds orbiting the nearest stars. And then there's the solar gravitational lens concept I mentioned earlier. If we can position a telescope at the focal point of our Sun's gravitational lens, roughly 650 astronomical units away, we could theoretically image exoplanets with enough resolution to see continents, oceans, and weather patterns. We might detect artificial lights on a planet's night side or geometric structures indicating intelligent construction. Imagine launching an interstellar probe already knowing that its destination hosts a living world with an oxygen atmosphere and liquid water oceans, or knowing that the planet shows signs of technological civilization. The mission transforms from speculative exploration to targeted investigation. This suggests an interesting strategy. Invest heavily in remote observation capabilities first, identify the most promising targets with high confidence, then launch interstellar missions optimized for those specific destinations. The observational groundwork might take decades, but it would dramatically increase the value of eventual missions. Let me address a question that arises whenever interstellar travel is discussed. Why bother sending physical probes at all when we can learn so much from telescopes? It's a fair question. Remote observation is enormously cheaper and faster than physical visits. We've learned tremendous amounts about distant galaxies, exoplanets, and cosmic phenomena without ever traveling there. Why not continue this approach indefinitely? Several reasons argue for eventual physical exploration. First, some measurements require proximity, detailed analysis of planetary surfaces, subsurface oceans, atmospheric chemistry at ground level, and especially any search for microbial life requires being there. Telescopes can tell us a lot, but not everything. Second, physical presence enables interaction rather than mere observation. If we find microbial life, we'd want samples to analyze. If we find technological artifacts, we'd want to examine them closely. If we find a habitable world, we'd want to explore it directly. Third, sending probes represents a commitment that remote observation doesn't. It declares to the universe and to ourselves that humanity intends to become an interstellar species. The symbolism matters alongside the science. Fourth, physical presence is a prerequisite for eventual settlement. If humanity's long-term survival requires spreading to other star systems, we eventually need to move beyond observation to actual presence. Starting with robotic probes builds the infrastructure and experience for eventual human expansion. Finally, there's something philosophically important about extending human, or at least human-created presence across cosmic distances. We are the universe becoming aware of itself, to borrow Carl Sagan's beautiful phrase. Spreading that awareness across light years continues the grand story of cosmic evolution. Now let's explore a topic that bridges science and philosophy, the Fermi paradox, and what it might mean for our interstellar aspirations. In 1950, the physicist Enrico Fermi famously asked, "Where is everybody?" Given the age and size of our galaxy, if interstellar travel is possible and other civilizations exist, at least some should have colonized the entire galaxy by now. We should see evidence of their presence everywhere. Yet we see nothing. Silence. This paradox has generated dozens of proposed explanations over the decades. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations inevitably destroy themselves before achieving interstellar capability. Perhaps they exist but remain undetectable. Perhaps we're being deliberately avoided. Perhaps the galaxy is colonized, but we're in an unoccupied region. Each explanation carries different implications for humanity's future. If interstellar travel is essentially impossible, if some physical or practical barrier makes it forever unachievable, that would explain the silence. It would also doom our own interstellar aspirations. But most physicists see no fundamental barrier. The challenge is immense but not impossible. If civilizations routinely destroy themselves through war, environmental collapse, or technological catastrophe before spreading to the stars, that's a sobering possibility. It suggests we face a great filter that few or no civilizations survive. It implies our own future might be brief. If we're simply among the first technological civilizations to emerge in our region of the galaxy, that's more optimistic. The universe is still young. Stars will continue forming for trillions of years. Perhaps we're early pioneers rather than late arrivals to an already crowded cosmos. Whatever the explanation, the Fermi paradox haunts discussions of interstellar travel. Every proposed mission carries the implicit question, why hasn't someone done this before? The silence from the sky is either encouraging, suggesting the stars are ours for the taking, or deeply ominous, suggesting dangers we haven't yet perceived. There's a concept in futures studies called the Great Filter. It refers to whatever obstacle or obstacles prevent the universe from being visibly full of intelligent life. Either this filter lies behind us, in which case we've already passed the hard part, or it lies ahead, in which case we face extinction-level challenges we haven't yet confronted. The development of interstellar travel capability might itself be part of the filter. Perhaps very few civilizations survive long enough, remain stable enough, and accumulate sufficient resources to actually launch missions to other stars. Perhaps the challenge is so great that it represents a civilizational bottleneck few pass through. Alternatively, something about interstellar colonization itself might be the filter. Perhaps the journey is so dangerous that most missions fail. Perhaps target worlds present unforeseen hazards. Perhaps spreading across interstellar distances inevitably leads to conflicts that destroy civilizations. Or perhaps the filter involves something we can't yet imagine, some challenge that hasn't yet manifested but awaits us in the future. Artificial intelligence run amok, self-replicating nanotechnology consuming everything, physics experiments that accidentally destroy space itself. We don't know what we don't know. These grim possibilities might seem like reasons to abandon interstellar ambitions. Why invest in reaching the stars if we're doomed anyway? But I'd argue the opposite. If a great filter exists, our best strategy is to become as capable as possible, as quickly as possible. Developing interstellar technology increases our options, our resilience, and our chances of surviving whatever challenges emerge. A species confined to a single planet is vulnerable. A species spread across multiple star systems is nearly impossible to extinguish. The very act of pursuing interstellar travel might be how we pass through the filter. Let me pivot to discussing some of the specific research institutions and projects actively working on interstellar propulsion and mission concepts, because this isn't just theoretical musing. Real scientists and engineers are dedicating their careers to making interstellar travel happen. The breakthrough initiatives funded by billionaire Yuri Milner represent the most ambitious and well-funded private effort. Beyond Starshot, the initiative includes Breakthrough. Listen for SETI research and Breakthrough Watch for identifying potentially habitable exoplanets. The combined effort brings resources and focus unprecedented in the field. The Initiative for Interstellar Studies, based in the United Kingdom, continues work begun by the British Interplanetary Society decades ago. They've conducted studies on everything from fusion propulsion to world ship designs to the sociological challenges of multi-generational voyages. Their Project Icarus built upon the earlier Project Daedalus to design updated fusion starship concepts. NASA's Innovative Advanced Concepts Program, known as NIAC, funds early-stage research into technologies that could transform future missions. NIAC has supported studies on solar sails, laser propulsion, nuclear concepts, and more speculative ideas. While most NIAC projects never fly, they advance our understanding of what's possible. The Tau Zero Foundation, named after Poul Anderson's classic science fiction novel, advocates for breakthrough propulsion research. Founded by former NASA physicist Mark Millis, who led the Breakthrough Propulsion Physics program in the 1990s, Tau Zero connects researchers, promotes education, and works to accelerate progress toward interstellar capability. Universities worldwide contribute through physics departments, aerospace engineering programs, and specialized research centers. Organizations like the International Academy of Astronautics provide forums for researchers to share findings and coordinate efforts. This ecosystem of institutions, while still small compared to other scientific fields, is growing. More researchers are taking interstellar travel seriously as a topic worthy of rigorous study rather than science fiction speculation. One development that could dramatically accelerate interstellar timelines is the emergence of powerful artificial intelligence as a research tool. Machine learning and AI are already transforming scientific research. AlphaFold, developed by DeepMind, essentially solved the protein folding problem that had stumped biologists for decades. AI systems are discovering new materials, optimizing engineering designs, and finding patterns in data that human researchers miss. Applied to interstellar propulsion research, advanced AI might accelerate breakthroughs enormously. Imagine AI systems that can simulate millions of potential fusion reactor designs, identifying promising configurations in hours rather than decades. Imagine materials science AIs discovering new substances with exactly the properties needed for solar sails or radiation shielding. Imagine mission planning AIs optimizing every aspect of spacecraft design simultaneously. This possibility makes timeline predictions particularly uncertain. If AI capabilities continue advancing exponentially, research that might otherwise take a century could compress into decades. Problems that seem intractable today might fall quickly to superhuman analytical capabilities. Of course, advanced AI also carries risks that could delay or prevent interstellar travel. Misaligned artificial intelligence might pursue goals incompatible with human flourishing. Economic disruption from automation might destabilize societies. Competition over AI capabilities might trigger conflicts that set back technological progress. The trajectory of AI development over the coming decades will significantly influence when and whether humanity reaches the stars. This adds another major uncertainty to any timeline estimate. Let's discuss something I find personally inspiring: the cultural dimension of interstellar aspiration. Throughout human history, our greatest achievements have been preceded by cultural shifts that made them imaginable and desirable. The Renaissance preceded the scientific revolution. The Enlightenment preceded democratic revolutions. The space age was preceded by decades of science fiction that made rockets and astronauts part of the cultural imagination. Interstellar travel exists in our culture today primarily through science fiction. Star Trek, Star Wars, The Expanse, Interstellar, Arrival, and countless other stories have made faster-than-light travel and alien contact part of our collective consciousness. These stories matter. They shape what people consider possible, desirable, and worth pursuing. But fictional interstellar travel is mostly unrealistically easy. Warp drives, hyperspace jumps, wormholes all allow characters to cross light years as casually as we cross oceans. Real interstellar travel will be far harder, slower, and more consequential than fiction typically depicts. We need new cultural narratives that grapple honestly with what interstellar travel actually requires. Stories about generation ships where characters live and die without ever seeing stars change. Stories about the psychological challenges of decades in transit. Stories about the patience and persistence required to build infrastructure across centuries. Such narratives exist but remain niche. Kim Stanley Robinson's Aurora explores the challenges of generation ships unflinchingly. Alistair Reynolds' Revelation space series depicts civilizations adapted to relativistic travel. These works deserve wider attention as we collectively imagine our interstellar future. The cultural work of imagining realistic interstellar travel might be as important as the technical work of developing propulsion systems. We need to want this enough to invest the necessary resources, and we need to want it in forms that actually match physical reality. Here's something worth reflecting on. Every person alive today is part of this story, whether they realize it or not. The decisions we make collectively about research funding, international cooperation, environmental sustainability, existential risk mitigation, all affect whether and when humanity reaches the stars. The taxes you pay might fund research that eventually enables interstellar probes. The career choices you make might contribute expertise to relevant fields. The cultural attitudes you help shape might determine whether your society prioritizes cosmic ambitions. You're also part of this story in a more fundamental sense. You exist at a unique moment in cosmic history. For billions of years, life on Earth had no possibility of extending beyond this planet. Future generations might take interstellar travel for granted, as we take intercontinental flight for granted. But we live in the transition period, when it's shifting from impossible to possible. We're the generation that gets to wrestle with these questions while they're still open. What kind of interstellar civilization do we want to become? What values should guide our expansion into the cosmos? How do we balance immediate needs against long-term aspirations? These questions are ours to debate and begin answering. Future historians, perhaps writing from worlds orbiting distant stars, will look back at our era as the beginning. The choices we make now will echo across light years and millennia. If you made this far, make sure to give this video a like. Your help is the biggest fuel to get this channel going, and I'm sure you will love this other video at the left side of the screen. Scientists finally show how we might travel faster than light itself. Scientists discovered a loophole so massive it makes interstellar travel not just possible, but inevitable. From naturally occurring warp-like effects in supernova shockwaves to the connection between dark energy and warp field exploration. See you there.